We'll finish up the nuclear notes today, and we're going to start off with half-life, and then we'll do some calculations dealing with half-life. What a half-life is, it's an amount of time, period. It's an amount of time. And it's the amount of time that it takes for half of the material that you have to change. So it's a given amount of time. So like what Louis was saying is that if the half-life is 1 year, and say we start off with 100 grams of a substance, only 50 of it is going to react in that first year. And then at that point, after 1 year, we have how many grams of the original material left? 50 of it, 50 grams of the 100, or half of it. So in another year, only half of that material is going to react, and so on and so forth. However, theoretically speaking, it doesn't end, but it does. So for each half-life, and again, it's in a given amount of time, and it doesn't change regardless of how much of the material you have left. It's how much of the stuff reacts or is consumed. That's another way that you could phrase it. So we'll get to do some of those calculations, and I think I just kind of explained all that there. Here's a graph actually representing or demonstrating the half-life process. Now, in honors chem, we will not be using natural logs, but we could be using natural logs for this type of reaction. That's for AP. And I know that a lot of you haven't used natural logs yet, or have you? No, it's a math function. All right, so that's one reason why we're not going to do calculations dealing with natural logs, is because you haven't done them. But there is another way that you can do these types of calculations, and if your math teacher doesn't show you this way, you have it in your back pocket. So it's actually a pretty easy way of doing it. But again, I think I mentioned that I had a 100-gram sample. Well, here's a 10-gram sample of some substance, strontium. And evidently the half-life period is 29 years, so after that 29-year period, we have half of the original amount. Go another 29 years, we have half of the half. So after 2 half-lives, how much of the material do we have? You're going to have to be able to determine after 3 half-lives how much of the original material remains. After 4 or 5 half-lives, how much of the original material remains. And it's not difficult once you do it, okay? It's difficult right now because you haven't done it.
Question.
Yeah.
Do you give us the half-life, or do we have to figure it out?
In some cases, I will give it to you. In other cases, I'll have you determine that.
How do we do that?
Good question. We'll do it. Here's a practice problem.
To know how to use it.
That's exactly right. Let me go ahead and turn the lights on, and you guys have these questions in front of you. Equation, for some reason I didn't put it in your notes, or it's somewhere where I'm not finding it right off the bat. But here's the equation that you're going to need to use. We're going to have n. N is equal to the number of half-lives, the number of half-lives. And the way we determine that is we take the total time, and we'll do some problems with this, divided by the half-life amount of time. Okay, and I'll explain that here in a moment. And then the second component to this equation is whatever mass you start with times 0.5 to the n. And that'll give us how many grams or how many kilograms or the mass of the stuff remaining. Now, this right here, the 0.5, actually is 1/2. So however many half-lives. So let's just, hypothetically speaking, say that the half-life amount of time, okay, is 10 minutes. Okay, we'll make this easy. Say that we start off with a 10-gram sample, okay, and the total time in this case is, the total time equals 10 minutes. Again, I'm making this rocket science here.
You give this to us, right? Like on the question?
I will give you this and this, yeah. Okay, so let me erase that for a moment. So if I start with 10 grams, that's my original, and you may hear this term, parent nuclei. That's how much of the stuff that we start with.
Oh.
Times 0.5. Now we have to figure out what n is. 10 divided by 10 is equal to 1. So we take that, and make sure your calculator can get this. So type this in. So 10, and you don't have to type in the units. 10 times 0.5 to the first power. So again, this would be 10 times 0.5, and you would use the caret button. Do not use the EE button.
Okay.
No. Use a caret, and in some cases,
What's the carrot?
might look like this. Okay, and I'm trying to think of different calculators. Most of the calculators have a caret button that looks like a roof, or it looks like this.
I don't get it.
What number did you get when you finished?
I got 5.
And you should get 5.
Okay, wait.
Okay.
How did you get to 5 stage?
How'd I get this?
Yeah.
This is the half-life. So it's 1/2 of however many half-lives. So this is my multiplier. So if I have, say, 2 half-lives, then I'm going to go through 2 half-life periods. So if I start with 10 grams and I go through 2 half-lives, what should my value be here?
2.5.
2.5. And if you don't believe it, type it in on your calculator.
Wait, so the n, you just put the n as 10?
No. Your n is right here. It's your multiplier for that, your exponent. Okay. On page 9, number 1, practice problem number 1.
It's like half of number 1.
Okay, it's part of number 1. All right, let's all do this, guys. It says a certain nuclei has a half-life of approximately 30 seconds. We'll say that it is 30 seconds. What fraction of the original nuclei would remain after 5 minutes? Then it says you began with 200 grams of this nuclei. How many grams would remain at the end of the 5 minutes? So we have 2 components here. Okay, so let's go ahead and do this first. So let's find out what our n is. So what is our total time here?
5.
5 minutes. Okay. Now I will give you a warning. It won't always be the bigger number that goes on top. I might give you an amount of time that's a little less than 1 half-life. So be aware of which is which. All right, and then what is the half-life amount of time?
30 seconds.
30 seconds. Now again, if we're going to divide, we have to have a like unit. So what would that be?
Oh.
How many half-lives have evolved here?
Oh, 10.
10. Very nice.
He is on it.
You guys are the human calculator. All right, so we've gone through 10 half-lives. We start with 200 grams. That's our original amount. Okay. And again, we'll use this equation here where we do our times 0.5. Now we're going to go to the 10th power. So this should be a really big number, right? So like 0.195. Okay. Now think about this. It's gone through 10 half-lives. So if it's gone through 10 half-lives, it wants to know what fraction of the amount remains. So here we can say that we have 0.195 grams to get the fraction over 200. Okay, so I just had it in here.
It tastes like
So it's 1 over that.
Yeah. I prefer chocolate. Wait.
Okay, so that's how much remains. That's our fraction.
Are they all gonna want us to do that?
Maybe. Maybe I will want you to do that. Okay. Most of the time, now again, I won't get it to be this ridiculous. I promise. I might do up to 8, 16, 32nd. I might go up to 64. Okay. But you should be able to easily do this, okay, to determine how much. Can everybody do this?
Yes.
Okay. Everybody do this. Yes is the answer. Find out how many half-lives, and then start with your original amount, multiply it times 0.5 to your number of half-lives. Number 2 says a certain radioisotope started with a mass of 333 grams. Calculate the mass of this radioisotope after 7 half-lives have elapsed. Now this is nice because do we need to use this?
No.
No. but we just go right to it. So 333, number 2. 333 grams times 0.5, and it said 7 half-lives? Okay. And whatever that equals. Okay, I would hope nobody'd have any issues with that. So like 2.60? Okay. Number 3. I'm sorry, 3C. Oh, that's homework, my bad. Or I'm sorry, 3, I almost did your homework. 3, thorium. Everybody pay attention, this is a little bit different than the first 2 here. Thorium-231 has a half-life period of 25.5 hours. You perform research at a chemical lab and need to order 100 grams of thorium-231 for an experiment. Determine the number of grams that you would need to order of the parent thorium-231 sample so you can receive the 100 grams of thorium-231 for the experiment you are about to perform for your research. You plan on performing the experiment at noon on Thursday. The chemical supply company can promise delivery of the material from Brazil, yes, the country, in exactly 48 hours. In the first 2 problems, you started off with a larger amount and it was reduced down, correct?
Yeah.
Yeah, so we found out, we started with 333 grams in question number 2, and after 7 half-lives, we only had 2.6, obviously not to scale. Well, in this problem, it's wanting us to do the reverse. We need to have this 100 grams at the end. Okay? So what we need to do is, we need to find out how much needs to be shipped if we know that it's 48 hours away. Okay? So if we need to order more, do we want to use this equation? Because we need to work backward.
No.
No, the answer is no. And this again represents 1/2. So if I'm working in the opposite, I'm going to take the inverse of this value, which would be that, which is equal to what? 2. Very good. So in this problem, instead of having 0.5 to the end, as we do here, in this case, our equation is going to have a little bit of a difference. It'll look like that. In other words, I've taken the inverse of 1/2, which is equal to 2. So, knowing that we're going to use this equation for this problem, now we can work.
Wait, are you going to give us that equation on the test too?
I will not give you this one. You just have to know that you need to take the inverse of 0.5, which will be 2. And I think you guys are capable of that. So let's write down a couple things that we know. So we need to find out what our n is.
Wait, quick question.
Yeah.
How do we know when to use the inverse one? Like, what's it going to say in this problem?
You'll need more. It's looking for more than what you started with. Okay, so if I need 100 grams, I need to know how much I had before it was shipped. So it's going to be a larger value. In other words, if I need 100 grams of it and you're shipping it to me from Brazil and it takes 2 days to get here, you're going to have to package a lot more than 100 grams. Okay. All right, so what is my total time? 48 hours, so 2 days. So, well, what's the half-life amount of time? Let's get on the same units there.
25.5.
Okay, so we'll go with hours. Okay. And the half-life amount of time for this problem is 25.5. And again, we have to have the same units. So, do we go through at least one half-life here?
Yeah.
Yeah, and that's a pretty good concept that I may ask. So in this place, or in this instant, we go, and we don't want to round too much, so if you have the ability to keep this in your calculator, that's a good thing. Okay. Now, we need 100 grams of this material, and so I'm going to use this equation because I need the packaging place to ship me more, so I'm going to do this. So 1.88235, whatever is in my calculator. And if you have an answer button, this is where it really comes into play. So anybody get like 369?
I got
368.675856. Okay, so the way I typed this in on my calculator, I actually did this first. Okay, so it's in my calculator. And then I did 100 times 2 caret answer button. Okay, if you don't know how to use your answer button, it's going to save you a lot of time.
How do I use my answer button?
Well, you have to do this first. 48 divided by 25.5. Leave it in your calculator. Don't clear it out. Okay.
Okay.
Then type in 100, and your answer will go away. 100 times 2 caret. Then do your answer. You might have to do second answer or something like that. Second, it's right over the equal sign.
Oh.
No, it's right over the negative sign.
Okay. And then hit equal.
Wow.
Six, so you got 368.67. Yeah, Renee.
I don't have an answer button.
Show me your calculator. It's next to the. Yeah, you don't have an answer button. So get a real calculator. I know. We do not. We're going to stop right there since it wants to know how much is shipped. Yeah. If it were asking what fraction, then yeah. But in this case, we're not. So the 3s are part of your homework? All right. And I'm going to go through this quickly and then get to the calculations since that's what you guys are longing for. Go ahead and get the blanks here. All right, I think I spoke about this a little bit yesterday or the last time we spoke. Nuclear reactions versus chemical reactions, there's a lot more energy released in a nuclear reaction than in a chemical reaction. And that's one reason why we harness nuclear reactions to help us to power homes and whatnot, because of the amount of energy that is actually released from that. So what we're going to do today is do some calculations where we can determine how much energy is released. This is the type of stuff that nuclear chemists would do. But also I do have a point here that nuclear reactions give off 1 million times more energy per gram of reactant than normal chemical reactions. That's pretty significant, pretty efficient, if you would say. Now, again, remember that energy is not created or destroyed, it just changes hands, so to speak. So it's not like we're creating this energy. All this energy is built up. Here's a graphic just demonstrating a chain reaction. You're not going to have to know how a chain reaction takes place, but do realize that once one atom is split, it releases other particles which slam into other things, and this takes place very, very quickly. Stop it. And once you get a nuclear reaction going, it won't stop until it finishes all the material. Okay. Go ahead and get biological effects of radiation. This is my warning to you all on being careful how much exposure you get in your lifetime. And I know some doctors are just crazy about, hey, let's take an X-ray. You're getting X-rays, and say you go to a dentist that's just crazy about, hey, let's get 4 more shots of that one tooth. It's like, really? You have enough. Okay, so just be careful is what I'm saying. When we talk about exposure to X-rays and other types of radiation, somatic versus genetic, you guys know the difference between that? You've all had biology. So somatic damage is like something that would occur on your arm or any other body part that deals with not next generation. So the genetic could cause mutations in the next generation. So be aware, be smart on how much exposure you're getting. Just going to a doctor and them x-raying this, that, and the other thing is ridiculous. MRIs, that's a totally different thing. That is not exposure. So MRIs, you can have all the MRIs. All right, the equation that we're going to be using for this one, and again, this is the first time you've used this. Again, E is energy, M is mass, C is speed of light. Speed of light, so it's a constant. And again, the 3.0 times 10 to the 8 meters per second. Okay. Now, the mass that we're looking for in this case will always be in kilograms. Okay? The mass will always be in kilograms. The energy that we're going to be looking at will be in kilojoules. I'm sorry, joules, not kilojoules. Joules. Yeah. But we could convert it to kilojoules if we needed to. There's one more thing, and this is given in your notes, that a joule is equal to a kilogram meter squared per second squared. So there's a lot involved in these calculations. But you'll have all of those things accessible to you. Okay? So keeping this in mind. Let's look at the first practice problem. It says calculate the amount of energy in kilojoules, so we'll do it with joules first, that is released in a nuclear reaction when the mass loss is 3 kilograms. Okay, so we have kilograms, we're looking for the amount of energy. Do we need to rearrange these variables?
Yeah.
No, because we're looking for energy. So we're going to use what we got. What is the mass of the substance here? 3 kilograms. So again, our mass needs to be in kilograms, and I'll explain that here in a moment. So we have 3 kilograms. And then the speed of light, again, is 3.0 times 10 to the 8 meters per second. And all of this is squared. All of that is squared. That's what the c squared deals with. Okay? So when we multiply this out, okay, we're getting a very favorable unit here. I'm going to, actually, this is how I'll type it in. I won't put the E there yet. It'll be 3 times, and I put this in parentheses, I don't put 3.0. 3 EE 8, and then caret, not EE for that one, 2. Okay. So it's 3 times this value squared. Okay. If I get like 2.17 or 2.7 times 10 to the 17. Anybody get that?
Yeah.
Okay. Now, what is my unit for that? What is my unit? It's kilograms times meters squared per second squared. Okay. That's my unit. Nobody's canceled out. And we also squared not only the number, but the units. So this is what my value is. Is this what the question's asking for?
No.
No. So what we need to do now is convert the unit. You have room. Okay. So 1 kilogram meter squared per second squared is equal to what? 1 joule. Okay. But do we need to finish with joules? No, we need to go to kilojoules. So again, if it's not the unit you're looking for, slide it. So who's bigger, a kilojoule or a joule?
Kilojoule.
So we assign the value 1 to that and divide it by 1,000. So in this case, it's 2.17 times 10 to the, I believe, 14. And that would be kilojoules. Okay. Again, this will be provided to you. The equation will be provided to you. These most likely will not be given to you, but you have to remember.
How many times it by 1,000?
I'm sorry?
The last one.
How did I know to do that?
Yeah.
Because I know that we need to get the joules to kilojoules, so to divide that by 1,000 to get me kilojoules. Because there's 1,000 joules in every kilojoule. Oh, while I'm thinking about it, 4B, cross that off. We haven't talked about them all yet. Don't do 4B, just 4A and 4C. Even though it says when 1 mole, don't worry about that. It's okay.
4A only?
4B is in boy. 4B.
No, only do 4A.
And C. And C. Even though it says mole in the problem, we don't do anything with that. So we're good. Yes?
How do you get 2.17?
Excuse me? Oh, I'm sorry. Yeah. Thank you. I was looking at the 17. You interrupted. Number 2. So it's essentially working the other way now. So let's calculate the mass in grams, so we get to go to grams on this one, of the nuclei that was lost when 3.33, so our energy here is equal to 3.33 times 10 to the 15 kilojoules. Okay? And the question wants to know how many grams. Okay? So, This is what was given. This is what we're looking for. Again, we will use this equation. If we're looking for mass, do we need to rearrange the variables?
Yeah.
Yes.
Very good. Okay, so how are we going to rearrange this? Good. We're going to divide the c squared on both sides. So we'll have this is equal to m. Okay. Now, we have to do a couple things before we start plugging in our values for energy. Can anybody tell me what we need to do to this first? Joules. Very good. So we need to change this to joules, because again, the conversion that we'll be using is this, so we can get our mass. So if you're given kilojoules, you've got to go to joules. Okay. So now we have 3.33 times 10 to the 18 joules. So 3.33 to the 18 joules. Okay. Speed of light, again, there's our equation. So we'll plug that in, and then we'll change the unit again. Times 10 to the 8 meters. And we'll square this guy. Seconds squared on the top. Okay. Now, is this a good unit? Joules times seconds squared divided by meters squared? I don't like that at all. But we can change the joule into this. Okay? So now we're going to rewrite it to look like this. And again, this is one of the reasons why it's very important to include your units. Changing the joule into kilograms, meters squared. I'm going to keep that all on the top. This is this. This is this. My seconds squared go right there. This still goes down here. And again, since we have joules, it's meters squared over seconds squared. Seconds squared goes down here. Look at that. Now, let's do the units real quick before we type any numbers in. What happens to the seconds squared? Gone. Can we cancel the meters out? Yeah, we actually have meters squared here. Do we have meters squared here? Oh yeah, meters are gone. What remains? What unit remains? Kilograms. Okay. So we'll have some number in kilograms, but that's not what the question's asking, of course. So when we type this in, we have to be really careful that we still have a square here. Okay? So I'll try to write it down here if you guys can see it. So 3.33 EE 18 divided, open up the parenthesis. Yes?
It says to the 15 power.
What's 15 power? That's kilojoules. We converted to joules.
Okay.
So now we're back. Okay, so 3 EE8, and then let's caret that right in there. Sorry? Oh, don't worry about it. You can write it on separate paper. Okay.
37.
37? Perfect. So 37 kilograms. So, how do we get it to our final answer? What's that? That's, oh no.
Convert.
Convert?
No.
Here, I'll move it up here.
I know, right? We can't just like erase something.
37 kilograms. So, kilogram here, gram here. Which one's bigger, kilogram or gram?
Grant.
Kilogram, very good. And there's 1,000 grams. So how many grams do we? 37,000. Wasn't that fun?
No.
Look at that. Look at that. You guys did your first equals MC squared equation. You go home and brag to your parents and say, look at me, I'm Einstein.